Let's look at one last conditional probability problem, and this is going to lead us into what we're going to talk about in the final section. So let's say we're screening for a disease, and it is generally known that 2% of the population has this disease. So a study of a screening test shows that the probability of having the disease and, remember this is an and probability, getting a positive test is 1.92%. Right? So that means if you pick a random person, a random patient, and before you even start thinking about the test, the probability that they both have the disease and get a positive test is 1.92%, whereas the probability that they have the disease, end of story, is 2%. Well, this should sound like a conditional probability to you. We're given probability of P for positive and D for disease is 0.0192, converting the percent to a decimal, and the probability of the event that the patient has the disease is 0.02, and so now we can calculate the probability that somebody gets a positive given that they have the disease is 0.192 divided by 0.02, which is 0.96, or 96%. So if we already know they have the disease, the probability that they get a positive is 96%. This is called a true positive. However, put yourself in the patient's shoes. You want to know if you have a disease, and you go in there and you get a test, and a positive comes up. Does that mean you have the disease? Well, this conditional probability doesn't tell you that, right? What we want is to reverse the condition and the probability. We want to know the probability of D given P. So I call this, I don't know if others do, but I call it the inverse problem. We want to switch the event and the condition. And that's what we're going to turn to in the next section.